So let's go ahead and look at the acid-base properties associated with salt solutions. Okay, so just as a quick reminder, what exactly is a salt? Okay, basically a salt is another name for an ionic compound. So stuff like NaCl, okay, or NaF, right? These are all examples of salts. Now, if I take a salt and I put it into water, it's going to break up into various ions. So NaCl, when it's dissolved in water, breaks up into sodium plus ions and Cl minus ions. Now, we know that these ions do have the potential of behaving as acids and bases. Okay, and so right now what we're going to do is we're going to look at how to identify which ones will behave as acids and bases and which ones will leave the solution at a neutral pH. Okay, so ions in solutions can react with water to generate H plus or hydroxide ions, and this process is known as hydrolysis. Now, the pH of the solutions can actually be predictive qualitatively, and basically that's going to depend on the salts, both the cation and anions that are present in solution. Okay, so an anion's ability to react with H2O is going to depend on basically the source or the relationship that anion has to an acid's strength. Okay, so if I have an anion X minus, and it is related to a strong acid in the form of HX, then this anion will have a negligible effect on the pH. Okay, and the reason why that is because when we look at the solutions with strong acids, we know that they ionize completely. Now, we know that the anions that are produced are going to be extremely, extremely weak bases. Okay, and with that being said, when you have that anion in solution, okay, it's not really going to want to interact with water. There isn't going to be an exchange of protons or anything of that sort. Okay, so since that doesn't want to happen, we know that anions that are related to strong acids are not going to affect the pH. On the other hand, if the anion that's produced is sourced from a weak acid, okay, as we see here, then there will be a pH change. Okay, and so basically what ends up happening in the case where the anion is sourced from a weak acid, you produce a conjugate base that is capable of behaving as a base in solution, and basically what you end up with is the following. So you're going to actually change your pH because you're going to put ions that affect pH into solution. Now, a complicated situation can sometimes arise when you have an anion that is produced that still has an ionizable proton. So remember, we've talked about polyprotic acids. Okay, well, we know that some of the products that are produced are still able to ionize certain protons. Okay, and so deciding whether or not the solution that contains these types of ions is going to be acidic or solution is going to depend on the Ka and Kb values. So if we basically look up our Ka values or our Kb values, and if we find that our Ka value is bigger than our Kb value, then the solution is going to be acidic. Why? Because this anion would prefer to behave as an acid. If Kb is greater than Ka, then the solution is going to be basic because the anion would prefer to behave as a base. So anions are not the only ions that can actually affect the pH of solutions. Polyatomic cations, such as NH4+, are also capable of basically creating pH changes in solution. And so we can look at NH4+ as being the conjugate acid of a weak base. And so therefore it can change your pH. Much in the same thought process as seen with the conjugate bases of weak acids. However, obviously it will have the opposite effect. Okay, metal ions can also interact with water and affect the pH. So we can see that here, aluminum plus 3 or iron plus 3. Basically what happens is that they chelate a bunch of water molecules onto that central atom. And what happens is that by bonding to this metal ion, okay, the ionizability of the hydrogen attached to this oxygen now becomes altered. And so because it becomes more ionizable, what ends up happening is the lone pairs on the water molecules that are still floating around can come along and basically abstract that hydrogen. Okay, and when it abstracts that hydrogen, it subsequently puts H3O plus in solution and basically decreases the pH of the overall solution. Okay, so as we can see, cations can also affect the pH of the solution. So let's go ahead and let's look at an overview. Okay, so guys, salts that make neutral solutions are going to be salts that are sourced from strong acids or strong bases. Okay, I'm not saying that we're actually taking those acids and making that specific salt, but basically if we take the individual ions and trace back the type of acid or base that they would be related to, then we can determine that they would not be a factor in changing the pH of solution. So if we look at, like, say, KCl, it consists of K plus ion and a chloride ion, Cl minus. Okay, and if we look at these two individual ions and we look at their sources with respect to acids and bases and where they potentially could have come from, we can quickly establish that K plus, right, could totally be sourced from potassium hydroxide, and Cl minus could totally be sourced from HCl. These are both examples of strong acids and strong bases. And so subsequently, the anion and cation that are put in solution are going to behave as either weak acids or very weak bases. So they're not going to really want to participate in the reversal of this process and producing, obviously, a stronger acid or a stronger base. Okay, so if we look at these sources or the acid and potential acid and base source of these various ions, we can obviously figure out that they would be either strong or weak. And depending on that solution, that's going to dictate whether or not the overall solution containing these salts is acidic or basic. So in these cases, obviously, these are all sourced potentially from strong acids or strong bases, so none of them would change the pH of a solution significantly. Okay, so salts that make basic solutions, basically, guys, if you have an anion in solution or in that's part of a salt that is the conjugate base of a weak acid, you're going to end up with a basic solution. Okay, so if we look at this situation here, okay, sodium acetate here, the acetate ion is going to be the conjugate base of the weak acid, acetic acid. So this salt can behave as a weak base in solution. So, the things that are going to be produced in solution or put into solution by this salt here are going to be Na plus. Okay, obviously we're going to have this acetate anion, and of course we'll have water in this solution. Okay, so we know that sodium ion is going to be sourced from a strong source, so it's not going to affect the pH. However, the fact that this acetate anion is from a weak acid, that's going to dictate that it's going to behave as a base in solution. So knowing that it's going to behave as a base in solution, we know it will react with water to produce a little bit of acetic acid and, of course, some hydroxide ion. Okay, and this is the Kb expression for this process. So let's go ahead and let's look at practice problem with something of this sort to figure out what the actual pH would be. Okay, so in this situation, they've asked us to determine the pH of a 0.30 molar sodium fluoride solution. Okay, and notice that they've given us the Ka for HF. Okay, now HF is the source, or is the acid source that's associated with the F minus ion. So how is this all going to come together? Well, the first thing we need to do is we need to decide, who's going to be actually affecting our pH. Okay, so we know Na plus is obviously not going to affect the pH because it's sourced from a strong base. Okay, but our F minus is from a weak acid, so we know that it's going to be affecting pH. Okay, but this is actually a base in solution. So really the process that we're trying to look at with respect to what's actually affecting the solution is actually a a base interacting with water. Okay, so we know that this is our base, this is going to be our acid, so this is going to produce the following. Okay, so these are our conjugate acids and conjugate bases respectively. Okay, and so we know that we're going to be putting some hydroxide into solution. Right, now the question is how much? Okay, well, in order to figure out how much hydroxide we're going to actually have in solution and how that's going to actually affect our pH, we're going to need to use the equilibrium expression. Okay, but the equilibrium expression for what we have going on in solution is going to be a relationship with Kb. Okay, so Kb is equal to HF, and then OH minus, okay, all over F minus. Now, notice we need to know Kb in order to go ahead and use our ice table and all the good stuff we've been learning how to do for the past little bit. So how are we going to get Kb? Well, we know Ka, and we've previously talked about the fact that the relationship between Ka and Kb can be looked at when you're dealing with conjugate pairs. Okay, and since these two are related, we can subsequently use this relationship to figure out our Kb value. Okay, so Kb is going to be equal to Kw divided by Ka, which in this case is going to give us 1.38 times 10 to the negative 11th. Okay, so this is our Kb value. So now that we have our constant, okay, we can set up our ice table and subsequently figure out what our hydroxide ion concentration will be, and that will then lead us to be able to figure out our pH and our pROH respectively. Okay, so we were told that we have basically 0.30 molar NaF. Okay, we know that sodium fluoride is a salt. It's going to ionize completely in solution. So we know that 0.30 molar is what we start with. Okay, our two species here, HF and OH minus, are going to be 0 initially, right? We're going to see these types of changes. Okay, so 0.30 minus x, and then x and x. Okay, so x squared over 0.30 minus x is going to equal 1.38 times 10 to the negative 11. Okay, so as we've done these problems a bunch of times before, we're going to make some assumptions about x. We're going to assume that it's very small. Okay, and we're subsequently going to basically have x squared being equal to 0.30 times 1.3 times 10 to the negative 11. And that's going to be equal to 4.14 times 10 to the negative 12. Okay, and if we take the square root of both sides, x is subsequently going to equal 2.0 times 10 to the negative 6th. Okay, and if we go ahead and check this, we find that we're way less than 5% with respect to error, so our assumptions over here in terms of dropping x were acceptable. Now, remember, x is going to be equal to the concentration of our OH minus. Okay, now, what they've asked us to solve for in this problem is pH, okay? But at this point, all I have is OH minus. So if I take the negative log of OH minus in this case, that's going to subsequently give us our pOH. And if we take our pOH and relate it via this equation, okay, we can subsequently find our pH, which is 8.31. So how has this solution been affected by having sodium fluoride salt dissolved into it? Well, instead of having a pH of 7, we now have a pH of 8.31. So what's happened is the solution has become more basic, which is what we would expect because this anion is reacting with water and producing hydroxide ion in solution. Okay, now there are going to be salts that make acidic solutions as well. So a salt where the anion is not a base and the cation is the conjugate acid of a weak base, that's going to lead to acidic solution. So an example of that would be ammonium chloride dissolved in water. Remember, chlorine is going to be sourced from a strong acid, so its conjugate base is not going to affect pH at all. Okay, but the ammonium ion, on the other hand, is capable of producing a pH change. So what's going to happen is we know that this ammonium ion is going to end up adding H plus ions to solution and subsequently giving us a more acidic situation. So similarly to the way we approached the problem that we did earlier with the sodium fluoride, we're going to do the same one with the ammonium chloride. Okay, notice instead of giving us the Ka value for something, they've given us the Kb for the conjugate base that's associated, okay, with the ammonium ion. And basically, we would just do the exact same approach that we did before. So we look at this ionization process. This is an acidic process. This is the expression that we're going to be using. We're going to use our Ka times our Kb equals Kw to subsequently solve for our Kb value, or excuse me, our Ka value. Once we have our Ka value, we're going to set up an ICE table just like we did before using our initial concentrations and basically solve for our H plus concentration using that ICE table. Okay, and you end up with 7.5 times 10 to the negative 6 molar H plus ion in solution and a pH of 5.13. Okay, so I advise you to go ahead and check this problem, go through the motions, and make sure you get the following answer. Okay, we also talked about other types of salts that can actually make solutions acidic. And those deal with the highly charged, very small metal ions, such as aluminum plus 3 or iron plus 3. So when AlCl3 gets dissolved in water, it actually produces basically this hydrated complex. Okay, and this hydrated complex subsequently allows, as we talked about, these H2O molecules to become basically more acidic. And when that happens, other water molecules can come and ionize those hydrogens off the water molecule, and you subsequently can put more H plus into solution. So this is just another problem very similar to the last ones. In this case, however, they've given us our Ka directly, so we don't need to use the Ka times Kb equals Kw relationship. Since we have Ka, we can then move on to figuring out the concentration of H plus for this ionization process. Okay, so basically we know that we're going to have Al, H2O, okay, and of course that's going to ionize into AlOH, H2O 5 plus 2 plus H plus. Okay, we're going to subsequently just use an ICE table. Okay, we know our concentration of our hydrated aluminum complex because this is a salt. It ionizes completely in solution, so it's going to pick up these 6 waters. Okay, we know the initial concentrations here are as follows. Okay, we know our ICE table looks like this. Okay, we know our equilibrium values. Okay, we know our Ka, so x squared over 0.01 is going to equal 1.4 times 10 to the negative 5th. Okay, notice I've dropped off the x here. We're assuming that it's going to be much smaller than 3% error to actually make this assumption. That way we don't have to do the quadratic equation. So that assumption subsequently gives us an x value of equal to 3.7 times 10 to the negative 4th. Okay, and I take my x value, and since it's directly equal to the concentration of H plus, I can just take the negative log of this value, okay, and that subsequently gives us 3.43 3.43 pH solution. So obviously our solution is much more acidic than a neutral situation, and as you can see, these positively charged cations can cause a decrease in pH of your solution. So what about more complicated situations in terms of their conjugate acids and conjugate bases present in the salt? Okay, so if we have a conjugate acid of a weak base, okay, that's our cation, and we have the conjugate base of a weak acid as our anion. So basically we have 2 things sourced from weak acids or weak bases. We then need to go and take a look at our Ka values. So if your Ka is greater than Kb, you're going to have the acidic situation. If Kb and Ka, if Kb is bigger than Ka, you're going to have a basic situation, and if Ka and Kb are equal, then you'll have a neutral situation. Okay, so an example of this. Okay, so ammonium acetate, okay, NH4. Okay, we just talked about ammonium being able to make the situation more acidic, the solution more acidic. Okay, and of course we talked about acetate, okay, being able to make the solution more basic. Okay, so which one's going to prevail? Well, I go ahead and I look up the Ka for NH3, and that's going to be 5.6 times 10 to the negative 10th. Okay, and I looked up the Kb for acetate, and it actually has the same value. So since Ka and Kb are the same in terms of their values with these two anion and cations respectively, we end up with a neutral solution. Now, if the Ka was bigger, then we would have an acidic solution. If the Kb was bigger, we would have a basic solution. So pretty much straightforward. You'd obviously need to hunt for a little bit more data, but you'd be able to get what you need.